Hi there, welcome to this lecture series on matrix algebra. This is lecture 28, part 1. The topic is an application of matrix algebra onto the relationship between matrices and graphs. Let's get started. So what is a graph? So a graph is basically a set, let's call it capital V, on whose elements are the followings, and you can have all these vertices. We label them 1, 2, 3, 4, 5, 6 in this example, and they are also called nodes. And then at the same time there is also an kind of a connection between the two nodes in the set. For example, from 1 to 2 they're connected, so we would draw a line, and from 3 to 4 they're connected, we would draw a line, and then from 4 to 6, for example, they're not directly connected, so there's no line between them. And then these unordered, so we're not saying from 1 goes to 2 or from 2 goes to 1. It's just like there is a road built between them you can cross. So these are called edges, and it's not ordered. So one can visualize them by drawing a straight line between any pair of nodes that has the edge connecting them. For example, as this left one here. So additionally, there is also another type of graphs where the edges are ordered, meaning that there is a direction that says from which node goes to which node can this edge be used. So look at this plot here. So we have nodes 1, 2, 3, 4, 5, and then we see that, for example, from between node 2 and 3 we have a path, but the path is only from 2 go to 3, not the other way around, and therefore it has an arrow. And you see all the paths has an arrow. And then you see that from 1 to 4, for example, and you could go from 4 to 1 and from 1 to 4, and therefore we will draw it twice with two different arrows on it. So such a graph is called a directed graph. In short, we will say it's a digraph. So we can also represent the graph by specifying the nodes and the edges. For example, this one on the left, we can notify all the nodes put in the set V, and then we see that they are just 1, 2, 3, 4, 5, 6. There are 6 nodes, and we number them. And then one can collect all the edges. Let's call it the set E, and that is a nodes that are connected, and the order doesn't matter here. Okay, so we'll have 1, 2, 1, 2 here, 1, 3 here, and 2, 3 here, 2, 4 here, and so on and so forth. We can collect all of them here. So these two sets here are equivalent to this graph here. And then for the digraph on the right, we can also collect in a similar way. So for the nodes, the set of nodes V, we'll have 5 of them numbered like this. And then the edges, that means the edges that are directed, called E. This will be a pair of nodes, and then the ordering matters. So you will have, say, 1, 3, that means from 1 I can go to 3, and 1, 4, and from 1 I can go to 4, and then you notice there's 3, 1, and then you can go from 3 to 1. Okay, so you can collect all of them and put here, and then these two sets also completely describes the digraph. So, of course, we will be seeking a different way of representing a graph. namely a representation of graph by using matrices. So this will be a symmetric matrix, and it's a so-called adjacency matrix. So let's explain. So let's say we have a graph with vertices v, and vertices are numbered 1, 2, 3 to n, so there are n vertices here, and I have a set E of edges. And then we can represent this graph by an m by n symmetrical matrix. We call it capital A with element aij. The aij's are assigned as follows. So aij would equal to 1 if the nodes I and j are connected by an edge, and it's 0 if not. Let's take the example of the graph we looked at earlier. So this graph here. So we see n equals 6. So we have a 6 by 6 adjacency matrix A here. And then you can go through all the edges. And let's say I have an edge connecting 1 and 2. And therefore in the position A12 is 1 and A21 is also 1, because if I is connected to J, then J is connected to I, and therefore this matrix is symmetric. Okay, so if this is 1 and this is 1 also, and then you can look at 2, 3, and then you find this one and this one, and then you find this one and this one. It's symmetrical, so this one and this one, you can go through all the edges and find them out. 5 and 6 are connected, then you have this one and this one. Okay, so this matrix clearly is symmetrical, and then there's also a property that the diagonal is all 0, because a node is not connected to itself by an edge. So similarly, we can also represent a digraph by an adjacency matrix. So let's see, we have a digraph with vertices in the set V. Let's say n vertices, they are labeled, and we have a set of edges E with direction. We can now represent this digraph by an m by n matrix A with aij as its entries, defined as follows. Aij equals 1 if there is an edge from I to j, and 0 otherwise. So note to the word from I to j. This hints there is a direction. It's not between I and j. That's why this is a digraph. Okay, so one thing to point out is that if there is an edge from I to j, that doesn't imply there's an edge from j to I. You will have to see if there is such a directed edge on the graph. So this matrix here, A here, is not necessarily symmetric, because aij does not equal to aji. Okay, let's take the digraph we have seen as an example to set up this matrix A. So A will be the following. So it has 5 nodes, so it's 5 by 5. And then we can look at each edge with the direction, and then fill this matrix with 1s on those places. Let's say from 2 to 3, that is a direction. So from 2 to 3, so 2 to 3, so we fill in the 1, and then 5 to 2, there's a direction, so we go down to 5 and 2, so this one. So you go through all the edges with direction and fill the matrix, those positions, with 1, and the rest will be all 0. So we see again that the diagonals of the matrix is 0, because a node is not connected to itself with an edge, with direction or not. Okay, so we want to stress again that in general, the A here is not symmetric. So what is the meaning of the adjacency matrix? Well, it tells you that whenever it has value 1, and there is an edge, so there is a pathway. So for example, if I pick a position here, that means 1 and 3. So this 1 means that the number 1 means you can take one edge and then you can go from 1 to 3. So you have that. And then for example, this 0 would be this is 5 and this is 1, which means from 5 to 1, if you go through one edge, there's no correction, so it's 0. So now we are wondering about the following question. What if I compute the square of this matrix A? I work out A times A, which is this thing here. Let's call this matrix B. So what does that matrix B represent? Okay, so let's write out B now. The element is B, I, J, I, K, and then B is A square. So we can write out B, I, K will be just computed as a inner product of the ith row vector times and the kth column vector of A. So if we write it out, it's the summation of these products. So what is the meaning of this value? So in fact, the value Bij here would actually be the number of passes of length 2 starting at node I and ending at node K. For example, let's look at the first one. So B11 is 2. What does it mean? That means for the node 2, you can find 2 different passes taking 2 steps and get back to 1. So from the graph you see that you can go to 3 and then you can go back to 1. That's one path. And the other one will be go from 1 to 4 and then from 4 to 1. So take 2 of these steps and you get back to 1. And then there are 2 of them. Okay. And say, for example, this one will be from, you're connecting from 2 to 1. So I want to connect from 2 to 1 going through 2 paths. How many ways can I do it? Well, I see that I can go to 3 and then from 3 I can go to 1, and that is the only path. So here is the theorem. If we have a matrix A is the adjacency matrix of a diagram, then if you look at the power p power of a matrix A to the power p and look at the entry ij of that matrix, what does that mean? Well, that basically means number of passes of length exactly p starting from the vertex I ending at vertex j. An application of these digraphs would be the ranking of different teams in a tournament or in a competition, for example. So let's say, here is an example. We have 6 teams playing several number of games, and between them, one wins and one loses. Let's say you can only win or lose. We don't have a draw here in this situation to simplify. So we draw a graph here where if you have an arrow from I to J, draw here, that means team I beat team J. So here team 1 beat team 2 once, and then team 2 beat team 3 once, but then team 4 beat team 2 once. Okay, so on and so forth. So finally we have a digraph like that, and the question is now, how can we rank them? Who would be the top team here. Okay, so one way of doing it, one possible way would be, let's say we write out the matrix A, the adjacency matrix. Then it looks like this. So one possible criteria of competing who is a better team would count the total number of wins, how many times you have won. That means we can add up, summing up all the rows. So I sum all that up, I have 2, and sum all that up, I have 1, and sum all that, I have 3, and so on and so forth. And what's the meaning of this vector, the number here? So the number here in the position k would be, for the kth team, how many times it won. So team 1 won twice. You see, it beat 2 and it beat team 4. And team 6, 0, has never won because it's only beaten by other teams, has never won anything. And then here we see that team 3 has won most number of times. Look at team 3. It beats team 1 and team 4 and team 6. Another concept of comparing this digraph would be the thing called the power of a vertex. So that is defined as follows. This would be the number of directed walks of length 1 or 2 originated at that vertex. So we are including length 2 also into this power. So how do you compute the power of the vertex? Let A now be the adjacency matrix of a digraph, and then we know the following. The sum of all entries in the ith row of K would be the number of walks. We call it walks. You can think in the example in number of wins, direct wins, okay? Walks of length 1, starting at I. And then if you compute a square, then if you sum up all entries in the ith row, what does it mean? Would be that will mean the number of walks of length 2 starting at I. So now it is clear that the power of the ith vertex is the sum of all the entries in the ith row of the matrix A plus A square. Going back to our example, we have the A matrix and we have the A square matrix all computed, and if we add them up, we'll get this matrix. And then we would add up the row vectors of each of these, so we get 6 numbers, and that's what we would get. And then we see that still team 3 comes out as the winner in this competition. We have reached the end of part 1. In part 2, we will talk in more detail about ranking of a digraph and its application in the ranking of websites on the internet. Okay, so exciting stuff. I hope you enjoyed this one, and now see you soon.